Every large-scale system has a baseline hum, a steady rhythm of application servers, databases, and caches doing exactly what they were engineered to do. But at enterprise scale, that hum becomes a roar. Imagine an infrastructure with 1,000 server pools. Each pool contains 100 machines, and every single machine is emitting 100 different operational metrics: CPU load, memory usage, request counts, constantly. That multiplies out to 10 million operational metrics generated relentlessly every single day. This chart shows metric writes over time. The dense points on the x-axis represent a constant heavy write load, but the read load behaves differently. When a dashboard refreshes, it requests massive, aggregated chunks of data. The reads are spiky and highly concentrated. We have a relentless heavy write load paired with a bursty, unpredictable read load. This core paradox dictates every architectural choice moving forward. The first instinct is often to route those 10 million metrics straight into a standard relational database, like MySQL or Postgres. But calculating a simple rolling time window average becomes a massive labyrinth of subselects and window functions in a standard SQL query. Compare that to a language optimized for time series analysis, like Flux. The exact same operation takes just 3 lines of clean code. The query syntax is only the surface of the problem. Under the hood, a traditional relational database fails to sustain the rapid-fire ingestion of 10 million daily metrics. The connection pool bottlenecks, disk I/O maxes out, and the primary node crashes. The required tool for this workload is a time series database, or TSDB, like InfluxDB or Prometheus. A time series database survives this extreme load by shifting the mechanics of storage. It relies heavily on in-memory caching to absorb the write barrage and utilizes low cardinality label indexing to group data logically. Relational databases are highly effective for transactional state. They lack the specific physics engine required to ingest, index, and compress raw telemetry data at scale. Before the database stores anything, we must extract the metrics from the raw application servers. There are 2 primary ways to build this collection layer. In the pull model, a centralized collector periodically scrapes data directly from web servers over HTTP. Since servers spin up constantly, it relies on a service discovery component, like Zookeeper, to actively map available targets. Alternatively, in the push model, application servers aggressively broadcast their own metrics outward. To handle spikes, metrics route through a load balancer into an auto-scaling cluster of collectors, ensuring the receiving end doesn't drop data. The pull method is highly effective for debugging and quick health checks, as you can manually query the server endpoints. The push method is required for short-lived, ephemeral batch jobs that execute and terminate before a pull collector can even detect them. Notice that in both setups, the collector cluster writes data directly to the time series database. This direct coupling between the collector and the storage layer is the single most dangerous architectural vulnerability in the entire pipeline. Consider the failure state of a direct write pipeline. What happens when the time series database crashes or goes offline for an hour of routine maintenance? The collector has nowhere to send the incoming telemetry. The data is dropped. You lose total system visibility at the exact moment your engineering team needs it most. We solve this by inserting a distributed message queue, like Kafka, between the collectors and storage. Kafka acts as a shock absorber. If the database goes offline, Kafka caches incoming data on disk and resumes when it recovers. We scale this buffer by configuring Kafka's partitions. By partitioning topics based on metric names, data is divided logically. This allows distinct streaming consumers, like Apache Flink, to read from isolated lanes and process metrics in parallel. These stream processors can pre-aggregate the data on the fly. They calculate sums and averages before writing to the storage layer, which massively reduces the final write load on the database. An observability system without a distributed message queue is literally a ticking time bomb just waiting for a traffic spike. Even with a perfectly decoupled ingestion pipeline, long-term storage introduces a harsh financial reality. Keeping 10 million metrics at a 10-second resolution for an entire year will rapidly consume an infrastructure budget. This chart shows granular data collected at 10-second intervals. It's necessary for short-term troubleshooting, but a storage liability. We keep raw data for 7 days, then downsample it. Compressing multiple granular rows into a single rolling average drastically reduces the storage footprint. Under the hood, the time series database further shrinks the data on disk using double delta encoding, a highly efficient compression trick that stores only the mathematical differences between timestamps rather than the absolute values. Finally, we place a dedicated query service cluster in front of the database. This isolates the read traffic, ensuring that aggressive dashboard refreshes from the engineering team do not steal resources from the ingestion pipeline. True data engineering requires knowing exactly when and how to selectively blur the details, preventing the storage layer from collapsing under its own weight. All this stored data is ultimately useless without an output layer, the mechanisms that notify the human engineers on call. But a naive alerting system is dangerous. If a server disk hits 90% capacity, it will continue to breach that threshold and generate a new event every 10 seconds. Repeatedly paging an engineer for the same threshold breach every 10 seconds rapidly leads to alert fatigue and ignored signals. This flowchart details the true purpose of the Alert Manager. It acts as a suppression firewall. It filters, merges, and deduplicates redundant threshold breaches into a single grouped alert before anything reaches an actual human. This brings us to the complete, battle-tested Observability Command Center. Raw metrics are extracted from the source, passed through the Kafka shock absorber, efficiently stored and downsampled in the time series database, and finally routed through a deduplicating alert manager. An observability pipeline succeeds by distilling billions of chaotic data points into a single, undeniable truth that an engineer can actually act upon.